In 2009, deep inside a Colombian coal mine, paleontologists pulled a fossilized vertebra out of the rock, and it was thicker than a human wrist. Their first assumption was a crocodile. Ancient crocodilians grew massive in that part of the world. But the shape of the bone was wrong. This wasn't a crocodile at all. It was a snake. A snake unlike anything ever recorded, one that would force scientists to completely rewrite the size limits of what a reptile could become. The site is called Cerrejón, and it isn't just a fossil bed. It's practically a time capsule. A tropical Paleocene rainforest, sealed almost instantly by mud and ash roughly 60 million years ago, just after the dinosaurs disappeared. Leaves, fish, turtles, an entire lost world preserved in extraordinary detail. As the team kept digging, they didn't find just one strange vertebra. They found dozens, along with ribs and matching fauna. The pattern was unmistakable. This wasn't a fluke specimen or an exaggerated fossil. It was a snake bigger than anything in the scientific record, and the researchers had a name for it before they'd even finished the math. Titanoboa. When they finally ran the numbers, they checked them again and again, because the math kept saying the same impossible thing. The final estimate: Titanoboa stretched somewhere around 13 meters, roughly 42 to 43 feet long, and weighed close to 1,100 kilograms, over 2,400 pounds. For comparison, the largest anaconda ever reliably documented reached about 8 to 9 meters and weighed a few hundred pounds. Titanoboa was nearly twice as long and several times heavier. So how do scientists size up an animal from a handful of bones? Modern snakes follow a predictable scaling pattern. The size of a single vertebra correlates closely with total body length. Paleontologists measured Titanoboa's vertebrae, compared them against living giants like boas and anacondas, and extrapolated backward from there. But that raises a much bigger question. Why was this snake so much larger than anything alive today? The answer isn't really about the snake at all. It's about the planet it lived on. Snakes are ectotherms. They can't generate their own body heat. Their entire biology, metabolism, growth rate, even their maximum possible size, is dictated by the temperature around them. A warmer environment means a faster metabolism, faster digestion, and the physiological room to sustain a genuinely massive body. Which means Titanoboa wasn't just a giant predator, it was a fossilized climate reading. And what it revealed was a world dramatically hotter than the one we live in now. Roughly 58 million years ago in the early Paleocene, Earth was still recovering from the extinction that wiped out the dinosaurs. In what's now northern Colombia, year-round average temperatures likely sat above 30 degrees Celsius, with essentially no seasonal cooling. No ice caps anywhere on the planet. No true winters. Just a rainforest that never stopped sweating, day or night. Here's the strange part. Even the Amazon, the Congo, Southeast Asia, the most extreme tropical rainforests left on Earth today, are actually too cool to produce another Titanoboa. Modern anacondas and pythons are already pushing against the upper size limit our current climate allows. To cross into Titanoboa's size range takes a planet running several degrees hotter, sustained for millions of years. Its enormous body needed that furnace-like heat just to keep its metabolism running and pump blood through more than 40 feet of coiled muscle. And the fossil site backs this up in vivid detail. Cerrejón has produced turtle shells the size of a small table, and early crocodile relatives with blunt, bone-crushing teeth built for hard-shelled prey, not sleek river hunters, but heavy ambush predators. This wasn't a clean, fast-moving river system. It was a humid, tangled swamp, murky water, poor visibility. Sound swallowed by constant rain. So how did Titanoboa actually hunt? Forget the movie image of a snake chasing something down. At over 40 feet, that kind of speed on land was never physically possible. That much muscle doesn't glide across a forest floor. It fights gravity with every single inch. Water changed everything. In the swamps of the Paleocene, Titanoboa likely behaved less like a typical snake and more like a crocodile. Slow, submerged, almost invisible. It could slip between fallen logs and root systems, its bulk hidden in tannin-stained water, barely disturbing the surface. For an animal this size, staying hidden wasn't a hunting trick. It was a way of life. It didn't chase prey. It waited, motionless for hours, maybe longer, until something came close enough. Biomechanical estimates suggest its coils could exert well over 400 pounds per square inch of constriction force, more than enough to crush a crocodile's ribcage almost instantly. Whatever it wrapped around had no realistic chance of escaping. Recent analysis of Titanoboa's skull suggests fish made up a major part of its diet, hinting at a largely aquatic lifestyle, rather than the classic image of a snake dragging prey off the riverbank. Alongside fish, its world was full of giant turtles and early crocodilians, slower, calorie-rich, and well within reach of a patient ambush predator lurking in the shallows. Water wasn't optional for an animal this size. It was essential. Buoyancy supported a body mass that would have been almost impossible to move efficiently on land. Out of the water, its own weight would have compressed its organs, making breathing labored and digestion painfully slow. And critically, water let it regulate its temperature, cooling off when needed, while still holding on to the heat its enormous metabolism depended on. So forget the image of a nightmare serpent thrashing across dry ground. The real Titanoboa moved in near silence, eyes just above the waterline, patient, waiting for exactly the right moment. If Titanoboa was this perfectly built for its world, why isn't it still here? The answer is almost anticlimactic. The world changed, and its biology simply couldn't keep up. After the Paleocene, global temperatures began a long, gradual decline. For a cold-blooded giant, that was catastrophic. Lower temperatures meant a slower metabolism, slower digestion, sluggish movement, and a growth rate that couldn't sustain a body this large. An animal that size needed constant, massive amounts of food, and a cooling world made that food harder to catch and slower to digest. In effect, Titanoboa starved in slow motion. Temperature wasn't the only problem. Mammals, tiny and largely irrelevant during the age of dinosaurs, were beginning to diversify, and unlike Titanoboa, they were warm-blooded, able to stay active even as the climate cooled. The swampy rainforests that had sheltered Titanoboa for millions of years were drying out. The giant turtles and crocodilians it shared its world with were disappearing too. The entire ecosystem that had made Titanoboa possible was quietly falling apart around it. It wasn't hunted into extinction. It wasn't struck down by disease. The planet cooled by only a few degrees, and that was enough to end the reign of the largest snake that has ever lived. Titanoboa never should have been possible. It was too large, too heavy, and entirely dependent on a climate that was never going to last. But for a few million years, every condition on Earth lined up perfectly. And in the flooded swamps of ancient Colombia, this snake ruled without a rival. Then, just as suddenly as it appeared in the fossil record, it vanished, leaving behind nothing but bones and a striking reminder of how narrow the window for life this extreme actually is. Titanoboa is proof that our planet has already produced monsters far stranger than anything fiction could invent. And the fossil record is still full of them, waiting to be found. If stories like this pull you in, hit subscribe so you don't miss what we uncover next. And down in the comments, let us know. Which part of Titanoboa's story surprised you the most? We read every single one. Until next time, stay curious about the world that came before us